Okay, here we've got a question. It says distributional approximations. So we're going to set up the correct distribution, but then we're going to use another distribution to approximate it. Okay, so more reading to do. It tells me what kind of approximation it's going to be, but for this kind of question you need to be able to recognize the distribution and the approximation. So let's look at what we're doing. We've got we want 5 left-handed people or more out of 40 people from this country. So we've got 40 people, and in this country 12% are left-handed. So I'm counting the number of left-handed people out of 40 people. So I'm counting successes from 40 trials, and we're going to assume they're independent. So if I'm counting successes in n independent trials, it means that my x, the number of left-handed people, so it's always a good idea to be clear about what your random variable actually means, and x will have a binomial distribution. Okay, what I really want is the value of n and the value of p. So my value of n, how many independent trials are there? It's the 40 people. And what's my value of p? Well, I want there to be 5. I know that 12% of the country are left-handed. I'll use the 5 later. 12% is a probability of 0.12. So if I want to use this posh notation, which sometimes you have to do, I need to put n first, comma, p after the comma. So that's my n and that's my p. Okay, so I've now got to find the probability that x is, so there are more than 5 left-handed people. So that's a probability that x is greater than 5. Okay, now if I wanted the exact probability, I could do this using my calculator with a binomial, but I'm going to use an approximation. So I've got to think about what kind of approximation. Well, n, which is 40, is good enough, that's large. And p, 0.12, well, that's not particularly small. So this is not too close to 0 or 1. So this is not close to 0 or 1. So we're going to be using a normal approximation. Okay, but even if you're using the original binomial, whatever you're doing with this, we need to do the outcomes diagram. So we've got 0, we were interested in values near 5, so 4, 5, 6, ... The upper limit is 40, but we don't actually need that. What we do need is our ticks and crosses. So we are going to say we want to be greater than 5, so I can't be 0, I can't be 4, I can't actually equal 5 because I've got to be greater than it, but I can be 6 or above. So with the binomial distribution, you do a big box and a little box. But the thing we're interested in now is the continuity correction that we need for our normal. Okay, so we can see that between 5 and 6, this is going to be a value of 5.5. Okay, right, let's set up our normal. So this is our exact distribution. Our approximate distribution is going to be, well, I need to find my parameters. So the parameters for a normal are mu and sigma. Well, let's do sigma squared. So mu, that's the mean, and the mean of a binomial is np. So what's my np? It's 40 times 0.12, okay, which is 4.8. And my sigma squared, formula for that, this is the variance. Formula for the variance of a binomial is np 1 minus p. That's page 11 of your formula book. So I've got to do 40 times 0.12 times 1 minus 0.12, which is 0.88. Okay, might need a calculator. Okay, so that gives me 4.224 is my variance. But remember, although we have to work with variance, we're often interested in the standard deviation. So whenever you get a sigma squared, also get the sigma. So sigma is the square root of 4.224. So on my calculator, I can do square root of that answer, and I get something stupid inserts. I get 2.0552. 2.0552. Okay, so I have my mean and my standard deviation set up for my approximate distribution. So my approximate distribution is that x is normal with mean 4.8, variance 4.224, but that means that sigma is 2.0552. Okay, so now I've got everything lined up. My probability of x being greater than 5, we've discussed the continuity correction. We're going from discrete, where 5 and 6 have nothing between them, to continuous, where on the normal I've got to find a cutoff between 5 and 6. So, for my normal distribution diagram, the centre of this in brackets is 4.8, and the value of 5.5, this cutoff between 5 and 6, I want to be greater than that. So I really ought to write down my probability has become x is greater than 5.5. The continuity correction means I'm not working with that 5, I'm working with 5.5. So now I've got a bog standard normal distribution calculation. I need a z. So z, of course, is 0 in the middle. I'm expecting this to be a positive z. I get z by doing the value x minus the mean 4.8 divided by the standard deviation. This is where I need to use 2.0552. If I hadn't recorded it carefully, I might end up using my sigma squared. I'd lose marks big time. So I've got a z value. There's a calculation. There's the value. So this is a z of 0.3406. Nearest makes no odds. Okay. And then for my probability calculation, I'm going to be needing to use that. This 0.3406 is going to be my lower, and I'm going to have an upper of 9999. There they are. Put that in, and I get a probability of 0.3667. And that is my answer to part A. Okay. Alright, so the remaining questions are going to be similar, but in each case they are changing the numbers. So in B, I've now got a 200 pupil school. So I'm now counting left-handers in 200 people. So n has become 200. Okay. So in part B, my exact distribution, the original distribution, so the exact one is x twiddles a binomial. Okay. N is now 200. So that's my n. P is still the probability of being left-handed. We're still in the same country. So this is still 0.12. Okay. So the parameters I need for my approximate distribution, my parameters, okay, my mu, my mean, is going to be NP, okay, which is going to be 200 times 0.12, okay, and my sigma squared is going to be NP1 minus P, which is 200 times 0.12 times 0.88, and if you work those out, they come to 24 for mu and 21.12 for the variance. Am I going to stop at the variance? No. Whenever we get a sigma squared, make sure we know what sigma is as well. So sigma, okay, is the square root of that 21.12. So on my calculator, it tells me that's 4.596. Okay, so I've now got the parameters I need for my approximate distribution. So my approximate distribution is going to be a normal with mean 24 and variance 21.12. So its sigma is 4.596, which is the one I want. Okay, now I've got to change the probability. So the probability is, I want the probability of having at least 30 left-handers. Okay, so I want the probability that x is at least 30. At least is greater than or equal to. Okay, outcomes diagram. 0 up to, don't care what the top number is, but I do care very deeply about values near 30. So 29, 30, 31, ... I need to be at least as big as 30. So that's a tick. I can equal 30. I can be 31. I can't be 29. So my big box would be everything. My little box would cut off here. And that's the bit I'm interested in. This cut off between the cross and the ticks gives me my continuity correction. So my probability of x being less than or equal, greater than or equal to 30 becomes the probability for the normal that x is greater than, what's the halfway point, 29.5. So now I can do my normal diagram. Okay, so middle of the distribution, the mean is for this one 24. My value here is 29.5. I need to get the z for this, so my z is 29.5 minus 24 over the sigma, not the sigma squared, the sigma, which is 4.596, which equals, my calculator tells me that equals 4.1967. Excuse me. So I've got a z value. I'm going to be using that z as, that's garbage. I've misread my calculator. This is a 1. Okay, otherwise it would have been much too big. Okay, so I'm going to be using that 1.1967, which looks right for this. This is a z of 0. This is 1.1967. That looks good. That's going to be my lower, and my upper is going to be 9999. And when I do that in the calculator, I get a p of 0.11571. So this is my answer. Okay. So let's have just a quick look at part C. So now I've now got 2,200 people in a village. Okay, I've now got a range of values 100 to 120. So I am going to leave to you, because I'm running out of space on my page, I'm going to leave to you the business of, at the beginning, setting up the distribution, the binomial and the normal, because that's the same as before. And I'm going to leave to you finding the probability at the end. Okay. But let's just go through the continuity correction. So this time, the probability is going to be x being more than 100, but less than 120. So all we're going to do in part C, or all I'm going to show you in part C, is the continuity correction. So the probability, x had to be more than 100, so 100 is less than x, is less than 120. Okay? But for the binomial, okay, that's discrete. I would have the diagram would be values near 100, 99, 100, 101, dot, 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 and I need values near 120, 119, 120, 121, dot, dot, dot. Don't really care about the maximum number. I want x to be greater than 100, so it's not allowed to be 0 or 99. It's not even allowed to be 100. It can be 101. It can be 119, but it's got to be less than 120, so it's not allowed to equal these and these. So my big box would include all the ticks, so I've got a value there. I've got a cut-off here, and my small box would get rid of all the crosses, so I can see my cut-off points for my continuity correction. The continuity corrected probability is cut-offs between 100 and 101, so it's 100.5 would have to be less than x, and the upper limit, 119 and 120, becomes 119.5. So you'd set up your binomial, you'd set up your normal, but then this one here is the probability you'd find from your normal. Okay? And if you do all of that yourself, make sure you set it out properly, just like we did in A and B. But the probability you should get is, well, before you get to the probability, you need z's, and they turn out to be minus 10.73 and minus 9.48. So, in fact, these are ludicrously large negative z values, okay, which means the probability your calculator tells you will be pretty much naught, okay? So maybe I'll change this question for future versions of the booklet, okay? So that's how we do C. Okay, don't worry that, I mean, in an exam they wouldn't do to that to you, because that's just a bit unexpected, isn't it? What have I had to assume in each case? So why would this not be valid? Okay, we go. Part D is asking what have I assumed, and I set up a binomial distribution. Okay, I know that I've checked my n and p each time, at least I should have done. I did it in the first time. All that happened in the other ones is n got larger and larger, so if 40 is large enough, the other ones were fine. That's not an assumption. It tells me what n is. So what it wants is a reason why the whole procedure is valid, and what I did is I set up a binomial distribution. Now, when do we get a binomial distribution? When we're counting the successes in n independent trials when the probability is fixed. Well, I'm told this 12%, so that's fixed, so the p being fixed isn't an assumption, that's given. So what I have to assume is that the trials are independent. So I have to assume that in this particular busload of people, the chance of one person being left-handed is not related to the chance of someone else being left-handed, okay? Which might or might not be true, but I've had to assume it. So in each case, I've had to assume that the left-handedness of people is independent. So left-handedness is independent from one person to the next, okay? So that finishes that question. So C was just kind of normal, except we've got stupid Z values. Don't worry about it.